Today we will discuss a pretty difficult problem, oscillations in a circuit with the diodes. But before that, please subscribe this channel because you will have opportunity to get this kind of difficulty every day. Thank you. Problem. The circuit in the figure consists of two capacitors with the capacitance C1 and C2. Two coils with the inductances L1 and L2, two ideal diodes D1 and D2, and the K key. Initially, capacitor C2 was charged to voltage U0. At the zero moment of time, the key K is closed. Questions. First, find the duration tau of the transient process, that is the time tau from which the process will become periodic. Second, determine the period big T of oscillations in a steady state. Third, find the voltage U1 and U2 on the capacitor C2 at those moments, time after the key is closed, when this current flowing through it goes to zero. Fourth, determine the amplitude A of the voltage fluctuations on the capacitor C2 in a steady state. Fifth, summarize the answers to the previous questions by qualitatively plotting the voltage U across the capacitor C2 versus time t between 0 and tau plus t. Mark on the graph the coordinates of the characteristic points, heights, lows, and the points of intersection with the axis. So, solution. First, let's analyze the situation before K is closed. So we have capacitor C2 has a charge, and the voltage on it is U0, positive on the lower side and negative on the upper side. When the key is open, it means that current cannot flow this direction, and because we have diode D1, this path is closed too. So current cannot go through any this or these directions. First question. Find the duration tau of the transient process, that is the time tau from which the process will become periodic. So first, what happened when we close this key? Now current can go through this key, and because we have here is positive and here is negative, current can go through this coil and through this coil. So this diode we can exclude like a regular wire and put here a regular wire. For this capacitor we have opposite picture. The current cannot go through this diode, it's still closed, and we have a circuit with a capacitor and two parallel connected coils, and in this case we have regular oscillation process with a easy calculated period. We have two coils in parallel, so we have this formula for period. This is inductivity for two parallel coils. But all this process will extend till charge on this capacitor is zero. It happened only during first quarter of a full period, because after that this diode will be open and current can flow through this diode and still through these two coils. let's write what is this first time. Let's say it's tau 1 when this diode became open. That's this one. Now let's see what happened during next period of time. When the charge on this capacitor became opposite, so this voltage became negative here and positive here, current start to move through this diode, and now we have two capacitors in parallel and two coils in parallel. So we can find what is period for this kind of oscillations. That will be this one. Two parallel coils and two parallel capacitors here. But all this process will continue till on this capacitor we have maximum voltage. So it means that after that this diode will be closed again, because now a current cannot go in opposite direction. That will be closed. So it means that this capacitor was charged in maximum, and after that we could be excluded from whole process. We will show why. Length of this second process will be again quarter of this second period T2. That's this one. Now when we have full charge on this capacitor, we have zero current here and full charge for these two parallel capacitors. So we can find what is total voltage on this capacitor using energy conservation. That's the formula. We have total energy in the beginning on this capacitor, on second capacitor, that's equal to full energy on both these capacitors. So we can count what is total maximum voltage on this second capacitors. We can call it U1. So that's the voltage on this second capacitor when we have zero current here, maximum charge here. Now, after this second process, we have currents start to flow in this direction, in left to this key through both coils. And now we have during this process only one capacitor C2 and two parallel coils here. So we can count what is total period for this kind of oscillation. Now after second quarter of period we have positive charge on the upper side and the negative charge on the lower side, and we have current which start to flow to the right through this key. So it can go this way, it cannot go through this second coil, and it cannot go through this diode and capacitor. So here we have only two elements for oscillations. That's capacitor C2 and the coil L1. In that case, the period will be T3 equal just this expression. And again, that will go through moment when we have a zero charge on this capacitor. And that's again a quarter of period, which is this one, tau 3 equal a quarter of third period. And now we have a process when we have zero charge on the second capacitor, and we have maximum current through this coil L1. And we can count what is this maximum current through L1. We can call it I1. We can use energy conservation, because whole energy from this capacitor going to energy to this coil. That will be this one. And now from this formula we can count what is current I1. That will be this one. So now let's investigate what happened during the next process. We have maximum current through this L1 which is going down, and now it cannot again go through this diode D1. It can charge capacitor C2, and it can and this current will split for other direction through diode D2. So current will go through L2, and we can count what happened during this process, because in this part we have current going through this coil, but we have opposite current which is going through this coil. This current will decrease, this current will increase, and the charge of this capacitor will stop when this current became equal to this current. So total current will be 0, and after that this quarter of period will stop, and we have this current will decrease, this increase, and this capacitor will start to lose the charge. So that's the process. And let's count in which time we have maximum voltage on this capacitor. It will be when in the moment when we have this current and this current will equal to each other. How we can count it? Due to electromagnetic induction, we have always voltage through this coil, and this coil is equal to each other. It means that the change of total flux will be the same. We have dF1 over dt equal dF2 over dt, where F1 and F2, that's a flux of magnetic field inside of these coils. And it means that if this is good for any moment, it means that this total change for any period will be the same. So that's our sentence for this period, the total change of first flux equal to total change of second flux. But we can count what is change of first flux. That will be a final current on this coil, through this coil, multiplied by inductivity for this coil L1, minus initial inductivity multiplied by initial current. So that's total change of flux. And the change of flux 2, it's just negative L2 multiplied by I. And they equal to each other. So it means that from this we can find what is current, final current I, equal to this and this. That will be this expression for this current. Let's count what is voltage on second capacitor in this particular moment, because now we have energy conservation, and we have total initial energy on the second capacitor. That's equal to final energy on this capacitor plus energy in these two coils. This is the formula. From here we can find, using expression for I, which we already counted, and using expression for U1, which we already counted, that will be this expression for maximum voltage on this capacitor. And the last step is to find out that this process will continue periodically. Let's analyze all this process for oscillations. So first we have full current through L1, which is charging this capacitor and splitting to this coil. So this current is decreasing, this current is increasing, and this charge is increasing till the moment when these two currents are equal. In this moment we have charge here is maximum, it starts to decrease, and means that currents still go this way, start to increase this current. So in the moment when we have total voltage is maximum, it starts to decrease. This current will increase, this current will decrease, till the moment when we have this current is maximum and this current is zero. But during this process, this diode always open. And we got the same situation as in the initial. So that's, it means that this process will continue forever, and this diode will never be closed. So this is the process. Now we see that the periodic process starts after time tau 1 plus tau 2 plus tau 3. That's the answer for question 1. Duration time tau. That's the answer for question 1. Now let's go for question 2, 3, 4, 5. Question 2. Determine the period t of oscillation in a steady state. So we already investigated that here we have a capacitor C2 and the two coils are connected in parallel. So it means that the period will be this one. This is a parallel connection for two coils, and this is our capacitor C2. Third question. Find the voltages U1 and U2 on the capacitor C2 at those moments time after the key is closed, when the current flowing through it goes to zero. And we already found this expressions. This is expression for U1, and this is expression for U2. Question number 4. Determine the amplitude A of the voltage amplitude on capacitor C2 in steady state. So we already found it. That's the same as U2. The only thing that during the third process that was just a quarter of period, but after this voltage reached this maximum meaning, the process became periodic with the voltage U2 equal this expression. And last question. Summarize the answers to the previous questions by qualitatively plotting the voltage U across capacitor C2 versus time t between 0 and tau plus t. Mark on the graph the coordinates of the characteristic points, highs, lows, and the points of intersection with the axis. This is the hour graph. First process starts from voltage U0, and it went to 0 point after time t1. That was a quarter of first oscillation. After that it was a quarter for second oscillation till maximum voltage U1, and after that it was third oscillation with time tau 3 till 0, and after that it started process with steady oscillations with a period t, big T. The only thing that we have to compare what kind of oscillations do we have here compared to regular oscillations without diodes. Because if we have regular without this diode, we have capacitor connected with two parallel coils, and the current in these two coils are going in the same phase. But in our case we have diode, and we see that current is not going in the same phase. When we have a maximum current here, we have zero current here, and we have a zero charge here. But after that we have charge is increasing, this current is decreasing, and this current is increasing. And when we have maximum charge on a capacitor, we still have a current on these coils, which we already counted. It's not zero, it's something. So this is the difference between regular oscillations and oscillation with this diode. Probably that's it. Thank you.